In a recent update that sparked renewed interest in China's carrier-based aviation program, an image of the J-15T fighter jet surfaced featuring a notable change. The engine nozzle revealed a domestically produced power plant, not the Russian-made engine typically seen on this model. The specific engine shown is believed to be the Taihang, a naval-optimized version of the WS-10 turbofan engine, marking a potential shift in propulsion strategy for China's carrier fleet. Observers believe the aircraft in the image is the prototype numbered 1518, previously showcased at the Zhuhai Air Show. Of the 70 or so J-15T aircraft believed to have been built, this prototype is so far the only one confirmed to use the Taihang engine. This revelation raises the possibility that a transition away from imported Russian engines could be on the horizon. Since the inception of China's modern fighter jet programs, Russian-made engines have played a pivotal role. The J-15T, China's carrier-based fighter derived from the Su-33 airframe, is currently powered by an engine based on the Russian AL-31F, specifically a navalized variant built for durability in maritime conditions. These engines were originally developed by the Russian company Saturn, part of the United Engine Corporation, and are known for their high performance. Their specifications include a maximum thrust of 122.6 knots with afterburner and around 75 knots at intermediate thrust levels. This model is no ordinary AL-31F. It includes enhancements designed specifically for carrier operations, such as emergency thrust modes and corrosion-resistant materials. These specialized engines offer features tailored for the naval environment, such as better resistance to saltwater corrosion, improved thrust for aborted landings, and more durable coatings for extended lifespans. Reports suggest their service life has been extended to approximately 1,000 flight hours through such modifications. Russia reportedly exported close to 1,000 engines of the AL-31 family to China, many of which were used in various platforms including the Su-27, Su-30, J-10 and J-15 fighters. Based on estimates, around 150 to 250 of these were naval variants intended for use with aircraft operating in maritime environments. That figure exceeds the current known inventory of J-15s, suggesting a surplus of engines is still in storage and awaiting deployment. The logical question many defense observers and aviation enthusiasts have raised is, if China has developed a naval version of the WS-10, known as WS-10H or Taihang, why hasn't it been deployed more widely? The answer lies in a mix of technical challenges, operational safety concerns, and production capacity. While the Taihang engine represents significant progress in indigenous engine design, it is still undergoing testing and has not yet entered mass production. Given the complex environment in which carrier-based aircraft operate, deploying an unproven engine at scale would introduce risk that military planners are not willing to take, yet. Carrier-based aircraft operate in one of the harshest environments for aviation: high humidity, intense salt corrosion, sudden temperature variations, and high mechanical stresses. Any engine used in this context must be specially hardened to withstand these conditions. Simply adapting a land-based engine with a few modifications is insufficient. The engineering requirements for naval aircraft engines are substantially different from those of their land-based counterparts. There are several key stressors. Corrosion resistance. Salt-laden air accelerates metal degradation. Naval engines must use advanced coatings and materials to resist this corrosion. Distortion tolerance. During launch or recovery, particularly with steam or electromagnetic catapults, rapid airflow changes can lead to engine distortion and compressor stalls. The engine must be able to withstand sudden variations in intake temperature and pressure. Overload resistance. The stresses placed on aircraft during catapult launches and arrested landings are severe. The engine's shaft systems and bearings must endure acceleration forces often exceeding 9 g. Anti-flameout capability. In high-speed maneuvers or high G turns, fuel supply to the engine may fluctuate. A well-designed naval engine must avoid flameout in these conditions. 4 protective qualities. Beyond performance, naval engines must be resistant to smoke contamination, mold growth, heat stress, and water vapor. Together, these factors explain why developing a carrier-ready engine is vastly more complicated than producing one for land-based fighters. The Taihang, while based on the mature WS-10 platform, still requires significant adjustments and prolonged testing to meet these stringent criteria. The J-15T represents a modernized variant of the original J-15, featuring compatibility with electromagnetic catapults, such as those equipped on China's newest aircraft carrier, the Fujian. With catapult-assisted takeoff, power and engine response become even more critical for mission success and flight safety. However, in the absence of a fully validated and mass-produced Taihang engine, the Chinese military has opted for the proven Russian AL-31F-based solution for ongoing fleet operations. This approach ensures reliability and operational readiness, particularly during a period of rapid naval expansion. Strategically, it also allows China to consume its remaining stockpile of imported engines, purchased with significant investment over the past 3 decades. Using these engines helps bridge the gap until the Taihang reaches industrial maturity. Unlike some other major aircraft engine development programs, such as the J-15 for the stealth J-20, the Taihang's path to deployment has been less visible but no less critical. Naval aviation is increasingly central to China's maritime strategy, and the ability to produce engines domestically will be vital for long-term sustainability and independence. If China can overcome the final technical hurdles and bring the Taihang into serial production, it would mark a major milestone not just in terms of equipment independence, but also in showcasing the country's growing aerospace capabilities. Until then, the J-15T fleet will continue to rely on Russian propulsion, offering a dependable solution for current needs while setting the stage for a shift toward full localization in the near future. With growing demand for carrier-based fighters and increasing investment in naval power projection, pressure is mounting to complete the transition to domestically powered aircraft. Future versions of the J-15, and potential next-generation carrier-based fighters, will likely be designed around the Taihang engine from the outset, simplifying integration and optimizing performance. Furthermore, the introduction of the electromagnetic catapult system on newer carriers such as the Fujian may reduce some of the stress factors traditionally associated with steam-based systems, potentially easing some of the requirements placed on the engine. However, until mass production of the Taihang becomes viable, China's carrier aviation program must continue navigating this transitional phase. The availability of Russian engines provides a safety net, but it is not indefinite. The evolution of China's J-15T engine strategy reveals the complexities of military aviation development, particularly in the maritime domain. While the end goal is clear, complete reliance on domestically produced components, the path toward that goal requires careful management of technical, logistical, and strategic factors. As the Taihang engine continues its trials, its success will represent not just a technological breakthrough, but a strategic achievement with long-term implications for China's military posture at sea. For observers around the world, it offers a window into how modern powers balance innovation with operational readiness in the race for maritime dominance.